And we're back. So we've wrapped up talking about section 5.1 on exponential functions. So we're going to go ahead and move into section 5.2. As a reminder, I'm taking for granted that you have that notes file I've posted available either alongside this video digitally or a printout. Either one's fine. The section talks about what we call logarithmic functions. That word can sound a little intimidating, but it's actually just a reskinning of the sort of exponential relationships we've already been looking at. Let's go ahead and dive into it. So the base format of a logarithmic expression is sitting right here. We have y equals the base a logarithm, I'll often just say log base a, of a number x. That's our format. And it turns out we can very directly rearrange this guy into the types of exponential stuff we've already been looking at. So I've got my double-headed arrow here because these two equations are in fact equivalent to each other. So we have a to the y equals x. So same parameters, just changing the positions to go from a logarithmic expression into an exponential expression. Let's take a look at a couple of examples of this in action. So we have 3 equals the log base 2 of 8. And I like writing it this way so we can just line up exactly where the various parameters are. So we have y is 3, a is 2, x is 8. So we have a, 2, to the y, 3, equals x, 8. 2 cubed is 8. You feel free to check that. So that's one example. The next one is a little bit trickier because we haven't had a ton of time to talk about properties of exponents, but I want to work through it just to make sure we're all on board. So we have 1/3 equals the log base 27, 3. So same setup. Our y is 1/3, our a is 27, x is 3. So translating into the exponential format, we have a, 27, to the y, that's 1/3. I'm going to leave a little space here, and then we have x, 3. Again, we haven't had a ton of time to talk about exactly how to translate an exponent as a fraction. Just as a reminder, hopefully this is will come back to you from your algebra memory banks. We can translate fractional exponents like this as roots. So this would be the 3rd root or the cube root of 27. And it turns out the cube root of 27 is in fact 3. You multiply 3 by itself 3 times in total, you're going to get 27. So examples. Great. So before we move on, I want to talk about a couple of really popular logarithms that end up coming up more often than most, I'd say. So let's take a look at them real quick, and then we'll dive in and play around with some other stuff. And I'm going to keep this up top because we're going to end up revisiting it again momentarily. But we'll often talk about what we call the common logarithm of a number. We generally write that log of x without any subscripts or anything at all. If you see this pop up in our context, that means a logarithm with a base of 10. So again, since 10 is kind of the basis for a lot of the stuff in our number system, hopefully that makes sense why you might call that the common log. So log of x means log base 10. On the other hand, we have what we would call the natural logarithm. So we denote that ln of x generally. And again, that's shorthand for a very particular logarithm. So the log base e of x, where e is that kind of funny 2.71828 number that we saw in the last section. Now, I wish I had more time to get into why we would call something that possibly unnatural feeling to you as the natural logarithm. To somebody who's been surrounded in mathematics as long as I have, it really does feel natural. If you want to do some independent research, I encourage you to do so. But for now, we're just going to have to kind of accept it. Log base 10, ln base e. All right? All right. So there's an example I want to take a look at where you might end up using this in practice. So we're presenting you with a particular logarithmic equation here where we have m equals 20 times the natural log of 40 over 40 minus s. So again, this whole thing is living inside this logarithm. The idea here is that m is representing the number of months since a product has been released. S is representing its corresponding market share after that point in time. So somebody in a marketing or research department has come up with this relationship describing those two quantities, market share and how long the product's been out on the market. So the idea here is we want to know how long we're expecting it to take to get to a 35% share of the market in whatever this product happens to be. Fill in whatever you like. So here we have an S value of 35. Be very careful on this. A handful of times in the course, we actually end up not converting a percentage into a decimal right away. This is one of those times. So be on guard as you work through a couple of the problems, when we're dealing with this logarithmic stuff. For some, we decide to leave the percentages as they are. So now I'm just going to fill in that value of 35 into this guy. And I got that, 20 natural log of 40 over 40 minus 35. 40 minus 35 is 5, and then 40 divided by 5 in turn is 8. So I have 20 times the natural log of 8. And if you work that out, grab your favorite calculating device. 20 times the natural log of 8 is going to give us approximately 41.6 months. So there's an example of how you might just use one of these things in a brute force calculation. I did want to mention, for those of you who have calculating devices, those common and natural log functions that I popped up here. I have my favorite TI calculator on display here. You'll see there's a couple of buttons, LOG and LN. Those do, in fact, correspond to the common and natural logarithms that we've talked about. So if you wanted to work out that ln of 8 and you had one of these bad boys sitting with you, you hit that ln button, then you tap 8, hit enter, and it'll give you a result. All right. So I did want to come back and take a look at this relationship just a little bit more because we can use it in some more concrete algebraic scenarios. So got a couple of examples I want to consider here where we're actually going to have an unknown, a variable we need to solve for floating around inside one of these logarithmic expressions. So for instance, we have the log base 4 of x equals 2. So we can take that. You could do some other stuff to try to solve for x here, but it turns out just translating this into an exponential expression will do exactly what we need. So again, we have a, we've got x. The 2 is standing in for this y right here. It's not written in the exact same order. Feel free to rearrange if you want to. So, but if we rearrange this, base a is 4 to the y, that's 2, equals, hopefully, 4 times, 4 squared is 16. So our x value in this instance would be 16. Another example of this in action, so if we have log base 3, a little more sophisticated in this instance, we have the log base 3 of 7 minus x equals, I'll still leave it 2. So again, we can convert this into an exponential expression. So our a this time around is 3. So we have 3 to the y, this guy over here by himself, equals the stuff on the inside. So I know there is an x there, but it's kind of standing in like this x in our original formatting. So we have 3 squared equals 7 minus x. So we have 9 equals 7 minus x. You do the same sort of algebraic machinery we've been working with since the beginning of the course, and we get an x value of -2 out of that guy. So a couple of these instances where we can end up using this logarithmic relationship to rearrange things and use the exponential behavior to our benefit. So I got one last example I want to take a look at. It's actually coming from the other direction. So we have 10 to the 3x plus 2 equals 0.25. You could write that as 1/4 if you prefer, but I'm just going with a decimal in this instance. So now I'm actually starting with something over here, and what I'm going to be able to do is translate it back into a logarithmic expression. And since the base of this thing is 10, I can actually use the base 10 log that appears, on my calculator. So the arrow is pointing vertically now instead of horizontally. Sorry. So now I have y. So that's going to be my, sorry. This is my x in this instance, because if I compare this, it's lining up right here. This is my y. So I'm going to have y, 3x plus 2 equals the log base 10. Normally I wouldn't write that, but I'm just doing it for completeness sake here, of 0.25. Now from here, this is really just a number. We can work this out. It's kind of an ugly number, but it's a number nonetheless. So you can, have this guy sitting over here, and now we just need to get x by itself like we've been doing for most of the semester. So now I will dispense with writing that base 10 because that's how I would type this into my calculator. I need to subtract over the 2. Then I need to divide the whole thing by 3. So if you do this step by step, that's fine. If you put it all into your calculator at once, be very careful to enclose the top of that thing in parentheses, or else the order of operations will get messed up and you'll just get this logarithm minus 2/3. You don't want that to happen. Anyway, so when we work that out, I got negative 0.8674. If you go to 4 decimal places, we didn't really tell you how accurate we wanted it, but that's the way to go there. All right, so that's kind of the baseline stuff I wanted to talk about logarithms. I'll be posting another video shortly where I talk about properties that logarithms end up happen to have, and we're going to use them to do some other handy stuff. Before I let you go in this instance, though, I did want to mention something about graphs of logarithmic functions. So there's a space on the very first page of the notes file that suggests the graph of a logarithm. I'm going to be posting into our Moodle course a graph I created in Desmos of a logarithmic function. So you'll see the general shape that most of them end up following, along with the graph of the corresponding exponential function. It's actually the base 10 common log and then 10 to the x. Okay, so you can see sort of the relationship where we're really taking the graph of one of those exponential functions and kind of flipping it across a diagonal line to produce the corresponding exponential graph. So stay tuned for more stuff about logarithms and how they can make our lives easier.